Primary colors are sets of colors that can be combined to make a useful range of colors. For human applications, 3 primary colors are usually used, since human color vision is trichromatic. For additive combination of colors, as in overlapping projected lights or in CRT displays, the primary colors normally used are red, green, and blue. For subtractive combination of colors, as in mixing of pigments or dyes, such as in printing, the primaries normally used are cyan, magenta, and yellow, though the set of red, yellow, blue is popular among artists. CRGB color model, CMYK color model, and RYB color model for more on these popular sets of primary colors. Any particular choice for a given set of primary colors is derived from the spectral sensitivity of each of the human cone photoreceptors. 3 colors that fall within each of the sensitivity ranges of each of the human cone cells are red, green, and blue. Other sets of colors can be used, though not all will well approximate the full range of color perception. For example, an early color photographic process, autochrome, typically used orange, green, and violet primaries. However, unless negative amounts of a color are allowed, the gamut will be restricted by the choice of primaries. The combination of any 2 primary colors creates a secondary color. The most commonly used additive color primaries are the secondary colors of the most commonly used subtractive color primaries, and vice versa. Biological basis. Primary colors are not a fundamental property of light but are related to the physiological response of the eye to light. Fundamentally, light is a continuous spectrum of the wavelengths that can be detected by the human eye, an infinite-dimensional stimulus space. However, the human eye normally contains only 3 types of color receptors, called cone cells. Each color receptor responds to different ranges of the color spectrum. Humans and other species with 3 such types of color receptors are known as trichromats. These species respond to the light stimulus via a 3-dimensional sensation, which generally can be modeled as a mixture of 3 primary colors. Before the nature of colorimetry and visual physiology were well understood, scientists such as Thomas Young, James Clerk Maxwell, and Hermann von Helmholtz expressed various opinions about what should be the 3 primary colors to describe the 3 primary color sensations of the eye. Young originally proposed red, green, and violet, and Maxwell changed violet to blue. Helmholtz proposed a slightly purplish red, a vegetation green, slightly yellowish, and an ultramarine blue. In modern understanding, human cone cells do not correspond precisely to a specific set of primary colors, as each cone type responds to a range of color wavelengths. Species with different numbers of receptor cell types would have color vision requiring a different number of primaries. For example, for species known as tetrachromats, with 4 different color receptors, one would use 4 primary colors. Since humans can only see to 380 nanometers, but tetrachromats can see into the ultraviolet to about 300 nanometers, this 4th primary color for tetrachromats is located in the shorter wavelength range. Many birds and marsupials are tetrachromats, and it has been suggested that some human females are tetrachromats as well, having an extra variant version of the long-wave cone type. The peak response of human color receptors varies, even among individuals with normal color vision. In non-human species this polymorphic variation is even greater, and it may well be adaptive. Most placental mammals other than primates have only 2 types of color receptors and are therefore dichromats. To them, there are only 2 primary colors. It would be incorrect to assume that the world looks tinted to an animal with anything other than the human standard of 3 color receptors. To an animal born that way, the world would look normal to it, but the animal's ability to detect and discriminate colors would be different from that of a human with normal color vision. If a human and an animal both look at a natural color, they see it as natural. However, if both look at a color reproduced via primary colors, such as on a color television screen, the human may see it as matching the natural color, while the animal does not, since the primary colors have been chosen to suit human capabilities. Additive primaries. Media that combine emitted lights to create the sensation of a range of colors are using the additive color system. Typically, the primary colors used are red, green, and blue. Television and other computer and video displays are a common example of the use of additive primaries in the RGB color model. The exact colors chosen for the primaries are a technological compromise between the available phosphors and the need for large color triangle to allow a large gamut of colors. The ITU or BT709-5/S RGB primaries are typical. Additive mixing of red and green light produces shades of yellow, orange, or brown. Mixing green and blue produces shades of cyan, and mixing red and blue produces shades of purple, including magenta. Mixing nominally equal proportions of the additive primaries results in shades of gray or white. The color space that is generated is called an RGB color space. The CIE 1931 color space defines monochromatic primary colors with wavelengths of 435.8 nm, 546.1 nm and 700 nm. The corners of the color triangle are therefore on the spectral locus, and the triangle is about as big as it can be. No real display device uses such primaries, as the extreme wavelengths used for violet and red result in a very low luminous efficiency. Recent developments in primary colors, color practice technology is usefully contrasted with color theory science because science assumes perfect conditions, whereas commercially available products must deliver impressive results at affordable prices. Some recent TV and computer displays are starting to add a fourth primary of yellow, often in a 4-point square pixel area, to get brighter pure yellows and larger color gamut. Even the four primary technology does not yet reach the range of colors the human eye is theoretically capable of perceiving, with four primary LED prototypes providing typically about 87% and five primary prototypes about 95%. Several firms, including Samsung and Mitsubishi, have demonstrated LED displays with 5 or 6 primaries, or color LED point light sources per pixel. A recent academic literature review claims a gamut of 99% can be achieved with 5 primary LED technology. While technology for achieving a wider gamut appears to be within reach, other issues remain, for example affordability, dynamic range, brilliance. An even bigger problem is that there exists hardly any source material recorded in this wider gamut, nor is it possible to somehow recover this information in existing pictures, as it was never stored. Regardless, industry is still exploring a wide variety of primary active light sources with the goal of matching the capability of human color perception within a broadly affordable price. One example of a potentially affordable, but yet unproven active light hybrid places a LED screen over a plasma light screen, each with different primaries. Because both LED and plasma technologies are many decades old and because sales are verging on $1 billion, both have become so affordable that they could be combined. Subtractive primaries. Media that use reflected light and colorants to produce colors are using the subtractive color method of color mixing. CMYK color model, or four-color printing. In the printing industry, to produce the varying colors the subtractive primaries cyan, magenta, and yellow are applied together in varying amounts. Before the color names cyan and magenta were in common use, these primaries were often known as blue-green and purple, or in some circles as blue and red, respectively, and their exact color has changed over time with access to new pigments and technologies. Mixing yellow and cyan produces green colors. Mixing yellow with magenta produces reds, and mixing magenta with cyan produces blues. In theory, mixing equal amounts of all three pigments should produce gray, resulting in black when all three are applied in sufficient density, but in practice they tend to produce muddy brown colors. For this reason, and to saving and decrease drying times, a fourth pigment, black, is often used in addition to cyan, magenta, and yellow. The resulting model is the so-called CMYK color model. The abbreviation stands for cyan, magenta, yellow, and black is referred to as the key color, a shorthand for the key printing plate that impressed the artistic detail of an image, usually in black ink. In practice, colorant mixtures in actual materials such as paint tend to be more complex. Brighter or more saturated colors can be created using natural pigments instead of mixing, and natural properties of pigments can interfere with the mixing. For example, Mixing magenta and green in acrylic creates a dark cyan, something which would not happen if the mixing process were perfectly subtractive. In the subtractive model, adding white to a color, whether by using less colorant or by mixing in a reflective white pigment such as zinc oxide, does not change the color's hue but does reduce its saturation. Subtractive color printing works best when the surface or paper is white, or close to it. A system of subtractive color does not have a simple chromaticity gamut analogous to the RGB color triangle, but a gamut that must be described in 3 dimensions. There are many ways to visualize such models, using various 2D chromaticity spaces or in 3D color spaces. History, a YB color model. A YB is a historical set of subtractive primary colors. It is primarily used in art and art education, particularly painting. It predates modern scientific color theory. A YB make up the primary colors in a painter's color wheel. The secondary colors VOG make up another triad. Triads are formed by 3 equidistant colors on a particular color wheel. Neither a YB nor VOG is equidistant on a perceptually uniform color wheel, but rather have been defined to be equidistant in the YB wheel. Painters have long used more than 3 primary colors in their palettes, and at one point considered red, yellow, blue, and green to be the 4 primaries. Red, yellow, blue, and green are still widely considered the 4 psychological primary colors, though red, yellow, and blue are sometimes listed as the 3 psychological primaries, with black and white occasionally added as a 4th and 5th. During the 18th century, as theorists became aware of Isaac Newton's scientific experiments with light and prisms, red, yellow, and blue became the canonical primary colors, supposedly the fundamental sensory qualities that are blended in the perception of all physical colors and equally in the physical mixture of pigments or dyes. This theory became dogma, despite abundant evidence that red, yellow, and blue primaries cannot mix all other colors, and has survived in color theory to the present day. Using red, yellow, and blue as primaries yields a relatively small gamut, in which, among other problems, colorful greens, cyans, and magentas are impossible to mix, because red, yellow, and blue are not well spaced around a perceptually uniform color wheel. For this reason, modern 3 or 4 color printing processes, as well as color photography, use cyan, yellow, and magenta as primaries instead. Most painters include colors in their palettes which cannot be mixed from yellow, red, and blue paints, and thus do not fit within the YB color model. Some who do use a 3-color palette opt for the more evenly spaced cyan, yellow, and magenta used by printers, and others paint with 6 or more colors to widen their gamuts. The cyan, magenta, and yellow used in printing are sometimes known as process blue, process red, and process yellow. Psychological primaries. Main article, opponent process. See also, natural color system, unique hues. The opponent process is a color theory that states that the human visual system interprets information about color by processing signals from cones and rods in an antagonistic manner. The 3 types of cones have some overlap in the wavelengths of light to which they respond, so it is more efficient for the visual system to record differences between the responses of cones, rather than each type of cone's individual response. The opponent color theory suggests that there are 3 opponent channels, red versus green, blue versus yellow, and black versus white. Responses to one color of an opponent channel are antagonistic to those of the other color. The particular colors considered by an observer to be uniquely representative of the concepts red, yellow, green, blue, white, and black might be called psychological primary colors, because any other color can be described in terms of some combination of these. See also, color theory, color wheel, secondary color, tertiary color, visual perception, notes and references. External links, Bruce McAvoy. Do primary colors exist? Handprint.com. The History and Science of Primary Colors, part of McAvoy's sprawling comprehensive site about color. Ask a Scientist, Primary Colors, the Color-Sensitive Cones at Hyperphysics, Color Tutorial.